Hello and welcome in this video where I'll be discussing the NVARC solution to ARC-AGI-2 2025. In summary, they are the winners of the Kaggle competition that ended yesterday on December 5th, 2025. So let's go into their paper. First of all, I'd like to mention that they have a video with the ARC-AGI organizers where they discuss their solution, but it isn't really a formal discussion. They just kind of give high-level ideas and intuition on what they did. So this is going to be more low level as opposed to that. If you want to know really quickly what is mentioned in that video, there's two takeaways since I watched the entire 30 thing to save you time. First of all, they said that reasoning and synthetic data generation are like two things which they would just do more, but it was restricted by the fact that Kaggle has a computation limit. And we'll talk about the model that they did end up using, in fact, which was essentially a compromise for this L4 times 4 GPU setup that was used in Kaggle. And then in order to once again have this compromise on restricted compute at the 12-hour inference time, they also moved the code generation and reasoning, which is used in at inference in times which are unconstrained, to like essentially prior to training. And how was this done? It was done through embedding this code generation and reasoning into synthetic data, which is to say that whereas at inference time, you can generate Python programs which will maybe augment the data or do things like this, they generated programs with H100s with GPT OSS at like before inference time, just offline, and made this synthetic data and then used the synthetic data to train the model online as if it was like baking in those weights that GPT or whatever, Sonnet 4.5 that they use, which we'll see, which they used. Okay, now what are the high level points here? First of all, the 4 billion parameter model of Qwen 3, which was the thinking version, was the largest model they were capable of using with the compute restraints. And second of all, within 1 month of training and making attempts on the data set, they realized that, let me see if I can find it in the document, with 1,000 training examples, they would quickly overfit. So after this initial month, they realized they needed to make synthetic data, which was the main push in the entire attempt. In fact, in the video that they do record, they mentioned that for like 2 months or something, there was no new attempts or no new submissions because they were simply working on generating synthetic data and not working on the method itself. So essentially the key was scaling the pre-training stage by appending high quality and more synthetic data. Therefore, the bottleneck in this competition was indeed the data. So this is the first thing, therefore, that they discuss. And it's a pipeline with 4 stages. First one is to collect puzzle descriptions and generate puzzle summaries. The second is to mix summaries and generate new, more complex summaries. The third is to generate Python code, which will generate input grids. And then the fourth is to generate Python code that generates output grids, so the answers to the inputs. And what's really important to note here is that this is all done offline, not inside of the Kaggle notebook, because as you can see, they use like Sonnet and Opus, which of course you can't use in the competition, and then GPT OSS 120B, which you could also not use because it would not fit in the constraints of the competition. Probably it could if you quantize it like hell, but then they don't want to waste compute on generating synthetic data, which they can just do offline. So this was not done offline. Once again, it was done offline. And now if we discuss the 4 parts in detail, right? We're going to do 2.1, 2, 3, and 4. We begin with the puzzle summaries, which are taken initially from the ARC dataset. And as they note here, it was surprisingly underestimated in the ARC community. So to be honest, I didn't even hear about this dataset before this paper. So it's pretty impressive that they used it. It makes sense with hindsight, but I don't know why actually others weren't using it. But in any case, it has, most importantly, solution attempts from 1,700 humans with the solution descriptions, which is what they want with these puzzle summaries. And then what they do next is quite interesting. They use LLMs to essentially make these puzzle summaries a standard rubric / template through these 5 parameters. If you want, you can pause and read what this says. And what you need to know is that this gave 716 times 3 summaries from this generation through Claude 4 Opus. And sorry, 716 from Claude 4 Opus, and then I believe 2 times 716 for 3 times 716 in total with GPT-OSS. I don't know what the difference is between these two runs, right? These two attempts. Maybe it's in the code and they had like a different prompt for creating this rubric. But in any case, it's worth noting that they had to resort to manual labeling because the generations were too easy. Where did they say here? Yeah, they were too easy. So they did 29 puzzles, and then they got tired, it seems, because it took 20 to 30 minutes puzzles. So this was like, they're spending between 600 and 900 minutes over these 29 puzzles, which is 10 to 15 hours. That's not a little amount of time. So then it looks like at that point, Claude 4.5 Sonnet had come out, right? And then they were like, okay, we're going to go back to code. So it's really interesting to see how their technique evolves as better models are released, because if Claude 4 Sonnet 4.5 came out, imagine that until from whatever, like August to November when the submission deadline was, let's like consider that no new LLMs came out, then maybe they would have still been manually annotating until the deadline. But that was not the case in any case. And what this means is that they were able to get 91 evaluation puzzles and 1,000 training puzzles from this Claude 4 Sonnet summary description. So I think they literally just said, Claude 4 Sonnet, give a summary for this puzzle. But that's my guess without seeing the code in detail. And in any case, you just should know that they had 3,268 summaries. And I will actually come and try to find those summaries for you here, because I realized that would be very useful. So let's come in to the repository and just search up for summary. Maybe this will be it. I actually haven't thought of this, but okay, there you go. Yeah, exactly. This is the format. So this is really great to see. I can't believe I hadn't thought of this earlier, but it's a great thing that I made this video. So if you guys remember, there was like the key insight, the puzzle concepts, tags, and input generation, solution steps. And if we come back to the PDF here, which is this one, then we see that we have equivalently like solution steps, input generation. So they use like just standard HTML tagging to get this. What are they actually doing? Okay, you're going to add system, synthesize. So, okay, this is just the template. It isn't actually an example, but this is nevertheless useful. You can see that they would put the input and output here. I see. And then this would be the actual comments on the puzzle, which gives it the human intuition, I guess, that is supposed to guide the reasoning. Some more prompting steps, which I'm not going to read now, but feel free to pause and read. And then, sure, concise summary of the transformation rules, which I believe is like for the specific puzzle. I don't believe, I know it is for the specific puzzle. Let's remind ourselves what was input generation. Step by step, okay, for creating. So this is how you create the input, and then solution steps is how you create the output, which is to say go from input to output. Okay, key insight, puzzle concepts. The rest of this is pretty standard stuff, but there you go. So this is exactly what's happening. And now, if we come back to what we were talking about here, we were just at the fact that, okay, we have 3,268 of these markdown files, and then we mix them. So they followed the InstructSkillMix idea to combine different skills. In particular, they prompted the LM to join two puzzle summaries and produce a new, more complex puzzle by combining elements from both. And this gave 266,593 puzzles from 3,268. And I just did 3,268, like the Cartesian product, which would be squared. And let's just remind ourselves what that was. I forget. Because it's much less than that, is what I'm trying to say. Okay, I don't know okay, there you go, 10 million, sorry. And they only had 266,000. So let's just I wish I could do this calculation off my head, but let's do like just 200,000, 1, 2, 3. So they only picked like 1.8% of the actual data that you could theoretically pick. And I imagine that this pruning happened. I don't imagine. Certainly, InstructSkillMix is what guided this pruning process to get from 10 million to 266,000. And of course, they didn't actually generate 10 million data points. I imagine there's some way of just only generating the ones which you believe would be useful, because that would be a lot of wasted LLM calls. So we can be certain on that. Now let's get on with the third and fourth steps, which is to actually make the grids themselves, which is the synthetic data. So the first step is to generate and filter the 266,000 logs to get 126,000 programs in Python. And how do they filter? First of all, they generate a Python program for the input grid logic, and then second, generate a program. Okay, yeah, this is valid. Let's talk about the input. I don't know why they're talking about the output grid logic in the input grid program section. Sorry about that. So to generate reliable and good input grid, they prompt the LM to produce additional unit tests for the input grid, such that you can compare these different programs and make sure that they're all consistently making the same grid based on the summary, right? Based on the puzzle summary, we generate the input grid logic plus additional unit test functions for the input grids. And then in post-processing, they filter programs which are capable of producing at least 30 unique input grids, and all of these grids pass all the unit tests. So I'm not gonna lie, I didn't look at the unit test and see what they did. If I just do a quick search and see what that would look like, maybe we can see something, but I doubt it's called just unit test, or I don't even know what it would be called, to be honest. Yeah, this is a exercise for the reader to go look at what those were like. But the only thing I want to highlight here is that when they made the summaries based on the training set, it was 70% of the puzzles that were generated passed the unit test, but when they made them on the eval set, only half, which is to say that the training is harder than the eval set. And this is a cool kind of validation of that. Okay, and then now we have these input grid programs, which are capable of generating at least 30 unique input grids. So these are not the grids themselves. I think I said that mistakenly. These are not the grids themselves. These are programs which can create at least 30 unique grids in a consistent way through these unit tests. Okay, and now with respect to the output grid programs, what are they doing here? In this time, instead of validating the Python code with unit tests, they keep solutions which transform the input grids equally. So where do they say this here? Yeah, which are, okay, we prompt LM multiple times for each input grid logic and filter out solutions which are not consistent, which are inconsistent. So we keep the solutions which transform the 30 grids equally. And they give an example which is really helpful here. If we say we generate 20 output grid programs for one input grid program, which is to say, like, there's one input grid program that can generate inputs, and then you're supposed to have a candidate output program which can take those input program generations and then map those to the correct output based on the summary, which is that markdown file. And if only 15 of these programs produce the same output grids, then you keep just those 15 programs, and the other 5 which are inconsistent, you discard them. And what this means is that you go from 126,901 input grid programs to, okay, no, here we're talking about puzzles, so let's not confuse ourselves. I think they actually mentioned it here. So they do get these 103,253 puzzles, which this would be a complex process, right? Because you start with this many puzzles, summaries, and then you have this many input grid programs, which can make at least 30, right? So in theory, you should do this number times 30. And I don't know how they're applying the summaries to each input grid program. So even though I said this is a low-level overview, it's not to the code level, unfortunately. But nevertheless, through this consistency check where you just make sure that they produce these same output grids, you are able to get 103,250 puzzles. And what you should note is that each puzzle has one input grid program and multiple output grid programs, but all of these output grid programs produce consistent output grids. Just like in the example where you have 15 that are mapped to only one input grid program. So I imagine that whereas there are 126,000 input grid programs, there are on the order of, actually I think they say it here, hold on. No, they don't say it. Also, yeah, they just say multiple. So like if we say that there's 5 output grid programs per input grid program, then we are going to have around 600,000 output grid programs. And then lastly, each synthetic puzzle has about 30 input-output pairs of grids. And this is tremendous because the max amount of input-output pair grids in ARC on the actual training and eval and anything that's released officially by the ARC dataset is 3. You can have up to 3 in your training set, which is designed to be by nature few shot, but here you can have up to 30. So more data is better. I think this is the principle that they would have applied here. And then once again, they use GPT OSS. Quite interesting to me that they did. I imagine it's just because they have a lot of H100s and probably not a lot of OpenAI credits. So, because in theory, those models should be better, but I imagine 120B is sufficient for just creating data. And in any case, they do have this unit test and consistency check, which which will make the results consistent. The only thing that potentially could be better if you're using like 4.5 Sonnet instead is that you can generate more difficult problems because it's a more sophisticated model. Okay, that was very long-winded, but it was very comprehensive, at least in my opinion. So I hope that was, a good outlook on synthetic data. Now let's talk about the architects. So the architects is a solution used in the previous year competition that is essentially just test time fine-tuning, which is to say that you have an LLM, you train it on a large data set pre-training, which is this one, with 3,255,481 samples, and then you also overfit on the test data while you're essentially doing inference on the Kaggle notebook. So this is the high-level overview of the architect solution, and because it is of a nature of just high data, high compute pre-training, and then your test time fine-tuning is limited by the Kaggle notebook, but you can still it's only used because the pre-training scales with the data size. It really has no effect. Like the fact that we are having the synthetic data doesn't really affect inference because we're not using the synthetic data at all at inference. We already have that baked into the model. So what we should know is in the pre-training, they use as many puzzles as possible in addition to their synthetic data. So I don't know actually which one is representing their synthetic data. I think it would be NVARC, right? So you have 55,000 unique puzzles here in the full, and then 47,000 in the training. I don't know really how this would map to, okay, I think, like literally 103,000 is the sum of these two numbers, so that makes sense. But then there are augmentations. So then you get this multiplier here. So you can think of augmentations as flipping on the XY axis, on the diagonal axis, if it's a square grid. And then you can also do color swapping. Another key change here is the fact that they only use a tokenizer with 16 tokens. So I forget how many tokens the initial tokenizer in the architect's approach used, but it was like, I don't know, like 20. I have this somewhere down, but they just found a more efficient tokenization approach, just less tokens, which use the Qwen3 formatting scheme. And this just makes your embedding table smaller. It's like probably a 0.1% improvement, but it is an improvement nevertheless. And then they use 4 8100 GPUs for 27 hours on the 4B thinking model with Qwen. And they use sequence packing of 256,000 tokens across 256 examples at max if the samples are small enough. If not, if the samples are too small, then you'll pad. And then if the samples are too big, well, I imagine that there's no case where the 256 will take up all 256,000 tokens. That would be like 1,000 tokens per sample. And this is a pretty... Actually, I don't know. I would have to see the tokenizer in action to make this assumption, so I'm not going to speculate for no reason. And then once again, you have the test time fine-tuning. It's pretty standard, except they don't use any gradient checkpointing. And just to recall, what is gradient checkpoint? It is recomputing activations at intermediate points within your model, forward pass and backward pass. Actually, I don't know if it's, I don't know actually which path or if it's both paths. I actually had a thing here, right? In summary, gradient checkpointing selectively recomputes a subset of intermediate activations to reduce memory usage during backpropagation. So it is only in the backward pass. And here you have a diagram which isn't helpful. But in any case, we know that they didn't use gradient checkpointing. And first of all, you need to note that gradient checkpointing is essentially you're freeing up memory, but then you're using up compute. So I imagine that with the 4 billion model, they had enough memory. So why would you essentially reduce your compute when you're already compute strained? So this is why they didn't use gradient checkpointing. And I think they said this specifically because the original approach did, and then they used flash attention too. I don't think this is really important to note because I think this is just the standard attention mechanism in Qwen 3 4B. So it's not like they did this. But in any case, now we have the depth first search decoding, which is a batched version. And once again, this is something that you need to look at the code to understand, which I haven't done yet. So just note that it's a way to sample tokens in order to get a grid that goes depth first and uses some probability mass as a heuristic to know when to stop and prune a specific tree. And then not only do you select with this depth first approach, but then you use additional augmentations to recompute the scores that you got from this depth first search stage with augmentations. I think that's what I said. Except instead of various augmentations in the ARC-AGI-2 approach initially, which led to up to from 8 to like, I don't know, 30 augmentations per trajectory where you generate a solution, they just use 8 augmentations, which I imagine, actually I don't know, because once again, I'm pretty sure you need to be square to be diagonal. So I'm certain that you have the horizontal augmentation, the vertical augmentation, and then rotations. Actually, does that make 8? We have this is 1. This is 1 degree of symmetry, and this is 2, so that's 4 already. And then you can have 4 different rotations. So that's probably the 8 type of rotations, because it's 2 times 2 times 2. Hold on. I'm not going to speculate on this either, but I'm pretty sure it would be the 4 rotations and the 2 flips. But I think that would actually give you 16 different augmentations. So they don't mention what type of augmentations they do use. In any case, this is just used to try to get a more consistent trajectory from each solution. But this is also not my field of expertise. So just know that they do rescoring to try to get more robust generations of grids. And then they have this graph here. So the only thing that I want to highlight here really quickly is that as you add more data, the loss descends sharper and will achieve a lower loss. Of course, they do stop these trajectories essentially not precociously, but too early. But you can see by the slope that it wouldn't have reached this amount anyway. So they have NVARC and NVARC here, but this run here has less data. And why is that? It's because they saw that the BARC dataset did not work well for the 2D transformer, so it actually hindered the performance. So they removed that. And then the last thing is that they do use, once again, this Qwen3 4B thinking, which was the compromise I mentioned, in order to still have reasoning, but just reasoning that is by default through the pre-training. And actually, no, this would have post-training for sure. But what I mean is that they're not inducing the reasoning. This is just the default reasoning that the model has, because you don't have the compute to do your own reasoning, it seems, in that Kaggle constrained notebook. The last thing I want to really mention is like the organizer in the paper for the ARC interview with the winners, which was NVARC. He was like, okay, what are you guys planning on doing for the next competition? And he said, well, it depends on how much compute you guys give us. So it's really fascinating to what extent their solutions depend on the constraints that the environment gives. Of course, you have to give constraints, but this is why like the unconstrained leaderboard with like Poetic and all these guys is much different than this leaderboard. So yeah, one thing that I haven't understand is that they said that, okay, we have Qwen3, the vision language model, which is 2 billion parameters. They said this results is our best submission, but I don't know what they were referring to, because like the 4B is both better on the evaluation, 25 versus 30, and on the public benchmark, 29 versus 22. Of course, it takes double the time. So maybe if they're considering time, then it's because of this that they said this is better. Or maybe I just misunderstood, but that's one thing I wanted to note. And then I'm going to skip over the tiny recursive model. This is more so of a topic on its own. And furthermore, they didn't actually use this method in their final submission because they just ran out of time, even though it looked promising. If I'll just show you, yes, they use this model. They use an ensembling, which is to say they combine Qwen3 2 billion with this, right? Qwen3 2 with TRM ensemble. And then they saw that, okay, their scores were getting good. And then where did they say that they didn't? Yeah, like we think that it would have upside, but it would require days, if not weeks, which we don't have. So essentially, if there was one more month, maybe this would have been their solution. But at the end of the day, they did not submit this as their winning solution, which got like, I think 27%. So yeah, once again, in the conclusion, to reiterate, scaling the pre-training stage with synthetic puzzles was the key here. This is why they have like not double, but like the next highest scoring was 16 and they have 27. So it is really remarkable given like As soon as you get to 5 steps down the leaderboard, like everybody has 3%. So it's impressive that these are like guys who are like, these guys are like one order of magnitude above the rest of the competition, which are definitely not incompetent data scientists, but of course not as competent as them. Yeah, so there you go. Let me know if you have questions on this. And yeah, I'm going to go more in depth on various ARC papers, so stay tuned for that.